With heat transfer, the driving force is temperature difference. Conduction, this is where heat is transferred by direct contact. Convection is the transfer of energy in a fluid or gas. And radiation is the transfer by electromagnetic waves, and the sun is the biggest source. R value is the resistive index, the degree to which a material resists the movement of heat. The higher the number, the better. Some countries use the U value, which is the insulation performance, and the lower the number, the better. Most of what we know about building science comes out of North America and Europe, where mostly we are concerned with keeping heat in rather than keeping heat out. But many of the same principles apply. This diagram is from the National Renewable Energy Laboratory of the United States Department of Energy. 15% of heat gain or loss in the building is through the floor. That is why it's common to install rigid insulation before pouring concrete. Doing this protects the concrete from moisture as well as creating a thermal break. It is required by building code in many countries. A thermal break prevents a thermal bridge and slows heat transfer by conduction. Under the floor of my house built in Thailand, sand was part filled, wetted, compacted, and the process was repeated. Then a vapor barrier was added, along with 3 inches of rigid foam. Despite the obvious advantages of adding foam insulation under the floor, it's not common in Thai builds. Walls account for 35% of heat loss or gain in a building. Concrete has an R value of only 0.1 per inch. Red brick R value is only slightly better at 0.2 per inch. Cement blocks or cinder blocks R value of 0.57 per inch. None of these materials would be considered insulating. Autoclave aerated concrete or AAC blocks have an R value of 1.25 per inch. But none of these compare with true insulation like closed cell foam, which has an R value of 7 per inch. Cavity walls give better thermal insulation than solid walls because the air gap between reduces heat transmission. The physics of cavity walls is a little complicated. Air is an insulator, but even in unventilated cavities, the air moves as a result of free convection. On the warm side of the cavity, air is heated, becomes relatively light and rises. At the cold side of the cavity, the air gives up heat to the cold surface, becomes heavier and drops. In this way, a circulation arises, which transports heat from the warm side of the cavity to the cold side. Adding foam to the cavity adds much needed R value, and the tiny pockets of air in the closed cell prevents convection. Adding foil prevents heat transfer via radiation. Building in Thailand, I couldn't source foil-coated foam, so instead I use double-sided foil insulation, which I attach to the inside of the outside wall to act as a radiant and moisture barrier. We attached 3 inches of foam to the foil with dabs of spray foam to create an all-important air gap between the radiant barrier and the foam insulation. Foam spray was used to fill any gaps and make an airtight seal. Then the inside wall was added. Painting the walls white reflects solar radiation. We added a wraparound roof to shade the walls and windows from the sun. Unfortunately, most people forget to calculate the ratio of glass to wall. Even the most expensive windows have a far lower R value than even an uninsulated wall. I chose to use glass blocks which have a far higher R value than the average window available here in Thailand, and they don't have poorly sealed window frames. My windows are small and set up high under the wraparound roof so no sunlight falls on them. To calculate the R value of any given wall, add the inches of each material used multiplied by their R value, and do the same for the windows. Then work out the percentage that you've used of each. 25% of heat is lost or gained through a roof. Here in Thailand, dark-coloured concrete roof tiles are very popular, and they act like a heat battery that charges up under the midday sun and releases that heat back into the house at night.
The reason we wanted the Department of Energy to take the lead in cool roofs is to demonstrate that this really saves money. If you have a roof and it's black, it's absorbing energy from the sun and it's getting hot. And it increases air conditioning bills, it does a lot of things. If you have a white or a reflective roof that scatters back the visible radiation, of course it reduces your energy consumption.
I used BlueScope ColorBond steel roofing, and they state the SA index or solar absorption for all the colors that they sell. I chose to use a bright white metal roof, and I also used a fly roof, sometimes known as a flying roof, which functions as a parasol by blocking sun without trapping any heat. The Passive House standard refers to houses that have met a number of very strict standards of energy efficiency and insulation.
When we talk about a building envelope, that basically means the walls, the roof, the floor, the doors and the windows. So we want to control the airflow in a passive house building envelope to control heat energy loss, to control unwanted heat gain, and to control infiltration of pollutants. And therefore, we actually do need a continuous air barrier around the building. In here, there is different membranes most likely, and then to connect all these pieces, we usually use high-performing tapes. We do air tightness testing with this equipment. This is called the blower door test. In simple terms, what it is a pressurization and depressurization test of the entire building. And you take one opening, in this case it's a door, we took out the door, to install the equipment, and it comes with a fan and it comes with a pressure gauge. So you can put in all your settings. You put in the area of the building, you put in the volume of the building, and then when you pressurize your building, you pretty much blow air into the building.
I recently had a conversation with a professor of architecture at a university in Bangkok, and I asked her why only one house in Thailand has achieved the Passive House certification. I also asked her if she knew where I could get hold of a blower door test. She wasn't able to help me. Leaks in the thermal envelope can be detected using a smoke gun or an infrared camera. Another product I wasn't able to find in Thailand during my build was Aero Barrier, which is like a tyre puncture repair system for a house. You positively pressurize the building, then blow in an aerosol caulking material and fill up any gaps.
This is a box, a kind of an all-in-one box that's going to mist out a caulking system into my air that's going to end up doing all kinds of air sealing and all those micro places where my envelope leaks.
In simple terms, what a thermal bridge does, it actually creates a pathway for the energy and the heat, which is the energy, to travel through the envelope from the inside to the outside. It's a continuous path for energy to go out of the building. So we heat our buildings, and right away it keeps on going out. So it's a huge factor for heat loss.
In cold climates, thermal imaging cameras take pictures from the outside. In this example, we can clearly see the thermal bridging effect of the stud walls. In hot climates, the thermal imaging cameras take pictures of heat coming into the building. This photo was taken inside a standard build house in Thailand, and we can clearly see solar radiation coming through the single glazed windows and the hot roof. I took this thermal image in my bedroom. The outside wall is south facing, but the windows are shaded by the wraparound roof. My bedroom is located on the ground floor with 3 inches of foam under the floor, in the walls, and on the floor of the second floor.
So by having a more airtight house, we're going to be able to control our envelope so that we can have better indoor air quality, better comfort, and of course, better efficiency. Now, I get a lot of people that say houses are too tight, but I would refute that and say, no, we want really good control of our envelope, and then we'll bring fresh air in on our terms, and we can filter it and we can distribute it.
If you insulate, you also need to ventilate, so I installed an energy recovery ventilator in my home. The inner core of my building is a conditioned space with windows that are sealed shut and doors that are well insulated. So it's important to bring fresh air in and take the stale air out. The fresh air is cooled by outgoing air-conditioned air, and then it is filtered. Incoming humid air passes humidity to the dry expelled air. The ERV will cool incoming air, filter it, and reduce its moisture content. So, why are all these doggies lying here by the doorway to the kitchen? Maybe because there's a nice cool breeze. Let's just have a look. Peaking at 2.5 meters per second. So that is air that is being sucked in to the living room and being drawn up and out up into the second floor and then out the top of the building. So this is effectively a chimney effect, and it's called stack effect ventilation.